So let's get straight on the topic. So this talk is on black hole mergers. Of course, primarily the all the detections which we have observed in the gravitational wave window and the challenges which we'll face ahead. Okay. So let's begin with the right. So let's begin with the groundbreaking discovery of the first binary black hole merger system, which we observed in the two LIGO detectors in the year 2015. So it was essentially a collision of two stellar mass black holes of mass 36 and 29 solar mass, which resulted into a remnant Kerr black hole. And this was the first binary black hole merger system observed. And after doing a very extensive analysis, we found that the system is made up of pretty massive stellar mass black holes, and which were located roughly at 450 megaparsec. And the system was highly relativistic. So you can see here in this plot that this is time and this is basically black hole separation. So as the system essentially evolves and goes towards a merger, it becomes highly relativistic. Uh, right. So and it was the perfect test bed to test the general theory of relativity. It was quite massive event and which emitted power almost equal to 3 solar mass, equivalent to the energy per unit time of 3 solar mass. All right. So with this discovery, is essentially, I mean, we could extract a lot of science from this event. So just to sort of bring out the unique features of this discovery, it was first direct detection of gravitational waves. It was first direct observation of the stellar mass black holes in a binary system. So we didn't know that such a system exists. Of course, it was, I mean, there were theories, and we knew that according to Einstein's general theory of relativity, if you have a system in a binary, and then it should essentially emit gravitational waves and eventually spiral in and then merge and form a compact object, right? But this was the first direct observation which gave clear signature of gravitational waves. And it was also the first direct evidence of existence of stellar mass black holes. This is particularly very interesting in astronomy because typically you observe black holes in X-rays through, let's say, accreting systems. And in astronomy, we have not seen systems higher than 25 solar mass. So this discovery essentially told us that there can be systems which with black holes higher than 25 solar mass. Of course, it was such a historic discovery that very soon the pioneers of the gravitational wave astronomy were rewarded with the Nobel Prize in Physics in 2017. Um, Right. So now I just want to give you few, the tests which we performed with this event. So we did essentially parameterize post-Newtonian test of GR. So since you have very well-defined system, it emits a well-defined signal, and according to GR, it carries the GR basically gives very clear signatures of the theory in the phasing of the signal. So this is the PN phasing. And what was done is essentially at each order, each post-Newtonian order, it was basically the phasing was tested whether it is consistent with GR. And such a test was, for the first time, it was carried out on this event, and it was quite consistent with the gravity. All right. Another test which was carried out was quite interesting. It was actually developed by a group in India in ICTS TIFR. So the idea which was the following, that you have, let's say, the binary black hole system emits gravitational waves in 3 phases. So in spiral, merger, and ring down. And the idea is that let's basically you can just take the signal uh, in the inspiral phase, and then you take the signal in the post inspiral phase, and try to essentially compute the parameters of the system. And using the parameters, the components, one can, in the inspiral phase, one can essentially use numerical relativity fits to sort of infer what is the final remnant mass and remnant spin of the black hole. And then you can basically get that information. So that is plotted here. You can see here, this is the inspiral information which you have got from the inspiral phase. And then you can do the same thing for the post inspiral phase. So here you are going to get information of the remnant spin and remnant mass of the black hole directly. And then you take the entire signal and try to ask the question, what is the the remnant mass and the remnant spin from the entire signal. So if all these parts are consistent with GR, then all of them should be the posteriors, okay, should be consistent within themselves. And that is what we have found, and that is what you can see from this plot. All right. So there was another test which was done essentially to probe the quasi-normal modes of the remnant black hole. However, I mean, this test was a little bit weak because we didn't have enough signal to noise ratio in this the first event. But basically, the idea is just to compute the quasi-normal mode frequency and the decay time. Okay, assuming that if you have a damped sinusoidal and ask a question like what is the posteriors of these two parameters. Okay, if you start from a particular time from the merger time. Okay, so and here also you can see things were consistent. However, I would say that the since we didn't have enough signal to noise ratio in the basically post merger phase, it was I mean, you can see that the posteriors are not, I mean, they're basically quite broad. All right. So now we ask the question. So this was done for the first event, and now we are almost like 5-6 years down. So we asked the question that, well, I mean, how do you improve this test and what has been done so far? Okay. So essentially, if you want to improve things, first is you need to have signals which are very loud. Okay, you need to have more signals. So in a sense, you should be able to probe much deeper in the universe so that you collect more compact binary mergers, and of course that will automatically probe a variety of signals, a variety of events with different masses and different spin properties. Of course, one can also design new sensitive tests which can probe different aspects of general theory of relativity. Now, in order to do all of this, what one needs is you need improved detectors and you need improved detection schemes so that we can essentially dig these signals inside the noisy data. So for that, you need to improve the sensitivity of detectors, add more detectors in the detector network, and also you need to have more improved searches to detect these signals. Okay. So yeah, some of these things were done over last 6 years, and the summary is here. So since 2015, we had 3 observational runs. The first run was from September 2015 till January 2016 with 2 advanced LIGO detectors. The second run was from November 2016 to August 2017, where the later part of the run, Virgo detector joined the 2 advanced LIGO detectors. And the third observational run was from April 2019 till March 2020. So this was right at the sort of beginning of the pandemic. And in fact, because of the pandemic, we had to cut down the third observation run. And this was with 2 advanced LIGOs and a Virgo. So you can see that there is some improvement in the sensitivity. So this is the detector sensitivity as a function of frequency. And in the second and the third observing run, there was some improvement in the sensitivity in the low frequency band. And when there is an improvement in the low frequency band, you can essentially get the longer in spiral phase of the signal, and as a result, you can sort of probe low mass systems better. All right. So with this, just little bit about the signatures of the compact binary gravitational wave signal. So essentially, we are talking about binaries with compact objects as in neutron stars and black hole systems, because those are the main primary target of the ground-based interferometric detectors like LIGO and Virgo. And essentially, the most vanilla kind of system would be that you have black holes which are aligned with the orbital angular momentum vector, and that essentially gives a very um, uh, simple kind of signal, which I had drawn somewhere here. Yeah, so you essentially get just the increase in the frequency and increase in as the time progresses, okay, and increase in the amplitude, and then you get merger and then subsequently ring down. However, if you have, let's say, spins are not aligned with the orbital angular momentum vector, then you get spin precession. Basically, there's a modulation in the signal, which is there are various examples I've shown here, which, and as a result, your waveform morphology is more complex. Okay. Of course, with the source location and orientation, there are some relative changes in amplitude and things like that. So this is the main sort of feature which we try to extract when we construct algorithms to detect these signals in the noisy data. Okay, so there are two broad uh, searches which we use in LIGO, LIGO Virgo detection. One is the model-based searches. So basically, general relativity predicts a given model for compact binary mergers, and we know how this model is characterized with respect to the component masses and component spins. Yes. Okay.
I think continue, go on.
Yeah, sure. All right. So essentially, we assume that we know the model, and then we try to correlate the data. So I'm going to play a little video. Okay, so here is a signal which is read in this blue data, and this is the template, or which is the model, which is basically constructed from the general relativity. From the general theory of relativity. I'm just going to play it again. And essentially, what we are doing is we take this template and correlate with this data. And if the shape of this template, I mean, this is a typical phase matching technique, which we call it as a match filter. If the morphology of this is matching with this, if there is a phase coherence, then essentially the signal acts coherently and the noise gets cancelled incoherently. And as a result, the place where the template matches with the signal, you will see the peak. So you can just watch again. Okay, so this is the template, and then you see the place where it matches, you will see a peak here. So this is the cross correlation result. And basically, this is the technique which we used in gravitational wave searches. Of course, typically the signal is characterized by many parameters. So if you take, let's say, spinning binary system generic, then it has 15 dimensional parameters. And if you try to sort of put the templates finely spaced in all these dimensions, then the problem becomes computationally extremely expensive. And as a result, typically we try to sort of capture only those parameters which are essential, or which essentially captures the main essence of the waveform morphology. Okay. Now, if and of course, and then you look for that template which essentially gives you the maximum output, and then that trigger is essentially selected and scrutinized for further study. Whether there could be cases like the template can match, let's say, noisy transient, and we try to check whether is it the case and stuff like that. Now, currently in LIGO Virgo detectors, we use templates with binaries having aligned spins. Okay, so we do not have any precision included in the template searches, and then as a result, the template search becomes also tractable. But and this is a typical template bank, which I have sort of it's a picture of that. It's a representative bank where you can see each point in this bank essentially represents a given template, and so you can see one has to essentially do the correlation over each and every point. Now, when you have as the number of templates increase, then the chance that it can also match with the noise triggers also increases, and this is what we call it as a false alarms. And we always need to assess what is what is the typical. So if you observe a particular event, then one has to assess uh, compared to this chance coincidence, and based on that we assign some significance to the event. Now, every run we essentially try to play with this various different techniques in order to reduce our false alarm rate, and then construct a particular detection statistic, because as the interferometers improve in the sensitivity, there are new kinds of noisy sort of transients enter our data, and one has to deal with it. It's more of an engineering thing which we do every time. So there are 3 searches which we run based on this template banks. Uh, so this is one search. The other search, which is essentially model independent search. And in this search, we do not assume any model of gravitational wave signal. And essentially you take the data and then we try to project it on the wavelet domain, which is characterized by time, frequency, and scale. And then you combine this information in terms of energetic pixels. So for example, you can map the signal in a time frequency map here, and then you collect the let's say energetic pixel, and then they are connected in a particular algorithm, and then we construct the event in a very multi-detector statistic way, and then we try to assign significance. And the advantage of this search is that it does not depend on the model, and as a result, if you have signals with very complex morphology, then this algorithm picks up very efficiently and very fast. In fact, the first event was detected by this algorithm first, and then it was followed up by other searches. All right. So now with these searches, what is it that we have seen so far? So here is essentially sort of the summary of the catalog. So we essentially, in the first observation run, we observed 10 binary black holes and 1 neutron star, binary neutron star. In the second observational run, up to that run, essentially our total number of events were almost 50. Okay, with 46 binary black holes, 2 binary neutron star, 1 neutron star black hole system, and 1 system which we couldn't sort of put them whether it is the component is neutron star or sorry, the remnant is whether it's neutron star or black hole. Okay, we'll come back to this later. And now this is the status we are now. So basically, we have finished analysis, and the third catalog is already out, and now we have close to 90 systems with lots of binary black hole systems, a couple of binary neutron stars, 3 neutron star black hole systems, and couple of systems are sort of, we couldn't place them where they are. It's essentially the components. So you can see that over the time, the gravitational wave astronomy window has sort of exponentiated in terms of the number of events, and that's also because of the improvements in the detectors which we had recently. All right, so I'm just going to now highlight few events and then summarize what the main features of these events, and then little bit about what kind of test of GR we did. Okay, so this was the first triple binary black hole system detected. It was an interesting system because it was the system when the Virgo detector started operating, and because of the three detector network, essentially we could measure the gravitational polarization for the first time. Okay, and the signal favored pure tensor mode as opposed to the pure vector and pure scalar. So it was the first time the test of GR, the polarization test of GR was performed on this event. Okay, so hence it is important. Of course, the sky localization of this event improved because we had one more detector, and that could sort of localize the patch slightly better than the two LIGO detectors. Um, the binary neutron star system was quite a remarkable event because it was the first event which where we observed jointly the binary neutron star merger event and the short gamma ray burst event in the Fermi GBM satellite. Okay, so it was exactly roughly 1.7 seconds the uh, after the detection of the binary neutron star event. It is the closest observed short GRB so far. Uh, and the whole point is, since there was a coincident event, I mean, there was a huge amount of science which we could extract. The first and foremost is that the short gamma ray burst puzzle was resolved with this observation. So gamma ray bursts are essentially very energetic sources in astronomy, and they emit a very huge amount of this thing is almost like 10 to the power 50 Earths in few seconds, and they are ultra relativistic and highly beamed. And for a long time, the source of this event or the progenitor of these bursts was unknown. And this coincident detection essentially gave a clear indication that the binary neutron star merger is essentially acts like a progenitor for the gamma ray burst. And with that, there was a huge campaign to observe this event, and close to 70 electromagnetic observatories were observing this event. And then with that, essentially, they could identify the galaxy. So there was a galaxy identification was made. So you can see here the burst appearing, which was, and with the galaxy identification, of course, we could get a independent estimate of Hubble's constant, because we could get the location of the galaxy, and then from the gravitational wave observations, once you know the galaxy, of course, you know the redshift, and the gravitational wave observation gives you inclination, and then one can sort of break the degeneracy between the distance and the inclination, and as a result, you can probe the cosmology, namely the Hubble's constant. So you can see that the Hubble's constant, which was predicted by 1708-17, essentially falls in between the Planck and Schuss. This was basically just from 1708-17. Later on, I will show you the new measurement, also including the black holes. All right. So the main implications of this 1708-17 was that it resolved the short GRB puzzle. Independently, we could estimate Hubble's constant. We could put constraint on the arrival time, on basically on the speed of gravitational waves, using the arrival time difference between the gravitational waves and the short GRB. And also the test of GR, like waveform consistency test was done. There were also constraints put on the equation of state of the neutron star with this particular event. All right. So then there were a couple of sort of asymmetric black hole binary black hole systems were observed. The first asymmetric binary black hole system was 1904-12, and essentially it was interesting because typically we see equal mass systems, because equal mass system essentially carries more energy, or more signal to noise ratio as compared to the unequal mass systems. And as a result, you basically probe much deeper, and hence I mean, it's more of an observational bias. We see more of equal mass systems. This was the first asymmetric binary black hole system was observed, and when you have asymmetric black hole system, you can also see higher order modes, higher than the quadrupole, and there was such probe of observing the higher order mode was done for this particular system. Okay, so the next system I would like to just brief upon is the 1904-25. So when we generally give this naming, this is 25th April 2019. So first comes year, then comes month, and then comes day. This system was essentially the heaviest neutron star observed so far. So if you look at this plot, okay, so this is the plot of the total mass of the binary system, and this dashed curve is essentially the distribution of total mass of the neutron of the binary neutron star, okay, in our galaxy, okay. So you see in our galaxy, whatever binary neutron star systems we have observed in the radio, basically in the electromagnetic band. So this is how the distribution is. And 170817 exactly falls here. Okay. But this system, okay, if you take the total mass of this system is somewhere here, it falls here. So it's almost like 5 sigma deviation from the binary neutron star distribution, uh, galactic binary neutron stars essentially, and that's kind of interesting because that is sort of I mean, poses questions on the binary neutron star systems formation itself, and hence this system was quite interesting. The system was essentially, it was not very nearby, so you can see the distance is almost 4 times farther than the 170817, which was at 40 megaparsec. We did not find any electromagnetic or neutrinos in other basically other bands, and yeah, so I think, and we could not localize this source also well because it was such a low signal to noise ratio system. All right, so this is another highly asymmetric compact binary system, and with this, in fact, we could get the clear evidence of the higher order modes, and hence this system is sort of is quite interesting. Uh, Also, uh, yeah, also we could sort of get the Hubble's constant using the galaxies in a given patch. Okay, so I mean, this was a very comparatively narrow patch. However, the Hubble's constant was not as constraining as one would get when you literally localize the galaxy, as was done for 170817. Right. So, right. So now we come to a different class of systems. So this is 21st May 2019, called a GW 190521. This system is very peculiar. In fact, this was the first binary system with the intermediate mass black hole remnant. Okay. So let's take a pause and just talk a little bit about intermediate mass black hole systems. So the intermediate mass black holes are essentially black holes which fall in between the stellar mass black holes and the supermassive black holes. So something like between 100 solar mass and maybe yeah, roughly a million solar masses. Okay. Intermediate mass black holes are very difficult to probe in the conventional astronomy. Okay, because I mean, just because I mean the black holes is very difficult unless like they are in the accreting system. Uh, but even in the accretion, when you have very so massive black hole, there could be I mean, there could be you know, other systems which can give the similar effects, and hence IMBH are always elusive kind of sources in astronomy. So 1905-21 was the first binary system with the remnant falling in the intermediate mass black hole mass range. Namely, the remnant mass was 142 solar masses, so greater than 100 solar masses. And this was the first direct evidence of the existence of IMBH with mass below 1,000 solar mass. So basically, there are candidates of IMBH in the electromagnetic window with masses greater than 1,000 solar mass. Okay, so besides the remnant being the falling in the IMBH, the components of these systems were also very interesting. So if you look at the system, this is 85 solar mass and 66 solar mass, which essentially merge into a final black hole of 142 solar mass. Now, these two systems, the stellar mass, the mass associated to that is quite high. And according to theories, basically the theory that it's very difficult to find to form black holes with this kind of mass. Okay, so when you have very heavy, let's say, star, okay, then uh, there is a gap. There is what is called as the gap falls roughly between 65 solar mass to roughly 135 solar mass. So you cannot form black holes. I mean, you cannot have black holes in this mass gap because the star becomes so unstable. Okay, that essentially it just evaporates if its helium core uh, is is very massive, basically. Okay, now if you take little bit higher massive stars, then they do fall. You can form black holes with that because they just collapse under gravity. So there is a small mass gap region, and according to experts, we don't expect black holes to be formed in that mass gap. And what we have found is that these two components, they fall into that mass gap, and that essentially I mean raises lots of interesting questions, is how these black holes must have been formed. So one possibility is that maybe these black holes themselves are remnant black holes of some other binary system which must have evolved, and then this black hole must have been formed. So maybe these two black holes are second generation black holes and not, the first generation. When I'm talking about generations here, we are talking about binary evolution and merger and so on and so forth. Okay, so hence this system is quite interesting. um, there are also other reasons why this system became more interesting, because this event, if you look at the event, it does not have any inspiral component. I mean, it's a very short signal, because sort of it trails towards the low frequency region of the interferometer, and it cannot, I mean, it does not spend enough inspiral cycles in the band, and as a result you do not see that inspiral nature in the signal. Okay, so now if that is the case, so it's a very short signal, and when you have a very short signal with not really loud, okay, there are other interpretations. So there are lots of interpretations of this signal, like maybe it's an asymmetric system, maybe it's a eccentric system, and so on and so forth. Okay, so this sort of poses challenge in the future, how to deal with the short duration signal. All right. So now with this, essentially we have gathered that the black hole formation. So far we knew that the black holes are formed basically, I mean, the black holes are the end stages of the stellar evolution. Okay. And with the detections of so many binary black hole mergers, now we know that there is an alternative channel, which is essentially mergers of black holes forming a new black hole, and maybe the next generation mergers forming the next set of. So basically, the hierarchy of mergers is another formation channel, and of course, the two formation channels might give rise to black holes which are having different properties. Of course, there are different environments in which the hierarchical merger channel sort of the formation triggers. So mainly, if you have a very dense environment, such as let's say galactic centers or maybe globular clusters, then these are basically very suitable environments for the formation, for the hierarchical merger channel. Nevertheless, these detections have opened up all these questions, and uh, and I think with more detections, we would get more clarity on the answers of the same. All right. So now I just want to show you the last set of events, which were binary neutron star, the neutron star black hole systems. Which, so in astronomy, in the electromagnetic astronomy, we have not observed binary neutron star systems, and it was not very clear whether they exist. And we have seen in fact, three neutron star binary, neutron star black hole binaries. And both of them did not have any electromagnetic counterpart, and couldn't have very clear source localization. And we expect that with more detectors, we might be able to observe these systems, more of these systems. Right. So, so this is sort of, I'm showing you this picture again. So now there are a few things to note, that if you look at this red dots, the red dots are essentially the X-ray uh, black holes, the black holes observed from the X-rays. And what we see is that the gravitational wave window essentially spans uh, the mass range of the X-ray black holes, the stellar mass black holes, all the way above. Okay, and essentially, so that is a very interesting thing, that we are able to probe black holes which are much higher in masses. As a result, we might be able to see a variety of black holes which were not really known to us so far. Okay. And also, the X-ray binary observations hypothesize that there might be a lower mass gap uh, from the stellar mass, the way it evolves, between 3 to 5 solar mass. In fact, we have observed systems in that mass gap. And of course, there are questions whether these are higher massive neutron stars or low mass black holes. So that is another question which is sort of opened up with these detections. Okay, so now what all things we have learned about the spins of the binaries. So essentially, we found that the mass, essentially, since the inspiral phase is essentially governed by a combination of masses, which is called as the chirp mass, and typically the chirp mass is better constrained. If you can actually observe the let's say the post merger, then you can actually constrain the total mass better. Okay, but essentially what we have seen is that we have observed systems with sort of better constraint on the chirp mass and lower values on this effective spin. So this effective spin is essentially is a component of the spin which is along the angular momentum vector, and these values are very small. That is what we have observed so far. Okay, it also tells you about how long is the signal if you have a spinning system. Right. So typically, if you have isolated black holes, okay, or black hole binaries, then you expect that as the time progresses, essentially the spin vectors tend to align with the angular momentum vector, and as a result, you see aligned systems. Okay, align this thing. But if you have, let's say, binaries in a crowded environment, okay, just like maybe in a dense environment, then essentially you tend to see spins which are randomly oriented. Okay, and so far we have seen mostly equal mass systems, mostly aligned systems. Okay, we have seen very few systems with essentially precision. Okay, so for example, this system, and this system. Okay, um, and so I think that is what it is. I mean, it's very difficult to conclude anything about the precision, because you need loud signals to really infer about precision as so far. Okay. However, there are questions regarding because the spins also give inputs on the formation channel, so it's interesting to sort of probe and understand. And when you have more systems, we'll know how the spin, how the two things are sort of linked. Okay, so with the black holes, we could also probe Hubble's constant slightly better than the 170817 by folding the joint sort of binary black hole and the but the main contribution comes from the binary neutron star system. Right. So now I'm just going to give a few tests. I'm not going to talk about all the tests which we did with the events. I'm sure I think there are other talks in this conference might tell a bit more about it. So the first is essentially parameterized post-Newtonian test, which was done on the first event. A similar test was done uh, with the catalog of events, and essentially we found that all the observations essentially they are consistent with GR. Okay, some parameters were better constrained, and for example, the high PN order parameters were less constrained because there is less information there. Okay, but the most stringent constraint was obtained on the -1 PN term, which is related to the dipolar radiation. Uh, there was a similar test was done with the inspiral merger ring down, right? Essentially comparing the inspiral and the post-inspiral signal, basically the probing the remnant mass and the mass and the spin of the remnant object, and the catalog events were found to be consistent with GR. So you can see that the deviation was consistent with the 90% credible interval, uh, coinciding for all the three catalog events. Okay. There was another test done which was probing GR with the quasi-normal modes. So here, essentially, you ask a question that you're trying to measure the fractional deviation parameters of the damping time and the frequencies. Okay, and this was done with 2 modes. Okay, using the Bayesian parameter estimation, these were sort of estimated, and these were estimated using the numerical relativity fits. And what was found was that there was no sort of frequency and the damping times obtained were consistent from that of the GR based NR fits. Okay. There was so there was the first time echoes were probed with the catalog. So essentially, the search for echoes. I mean, essentially, you are. Here just to give a background. So these are the you're trying to look for exotic compact objects without any event horizon, and that they would emit wave packets in regular intervals due to the multiple reflections of the incoming gravitational wave merger signal. And essentially, this was carried out using unmodeled kind of search framework. And when one the significance value was computed, and there was no evidence of the post-merger echoes was found with all these events. Besides that, there were other tests were performed. Okay, so namely the constraint on the mass of graviton was obtained. Okay, also the combination of different polarizations were probed, and no evidence of the non-GR modes was obtained, and there was no basically significant deviation from GR was obtained using these events. All right. So now with this, I reached to the last part of the talk. So now the future observing prospects. Essentially, our next run is scheduled to start by end of this year. This is the 4th observing run, and following that would be the 5th observing run, which will be with much higher sort of configuration. So you can see here. This is LIGO, and you can see O4 is this gray solid line, and then O5 is this magenta line here. And we expect that the distance reached for the binary neutron star would be something like 1.5 times in O4 compared to what we have now, and that would go to 3 times in O5. So as we improve in the distance, essentially our gravitational wave amplitude scales as 1 over the distance, and as a result, any improvement factor times cube is the rough improvement in the events we get, because that much times more volume essentially we probe. So we expect to see a large number of events, especially binary black hole events, also neutron star black hole systems, and neutron star binary system. Okay, so a similar improvement you'll see in O5 and O4 and O5. Yes, so basically, and with this, we also plan to expand on the network. So for example, the next run will be with the Japanese detector Sagra will join, and we expect that five possibly LIGO India will also join the network. As you include more and more detectors, we can actually localize the sources better, and that improves the prospects of doing multi-messenger astronomy, also constraining Hubble's constant. Um, so essentially, everything is just, we are just waiting to collect more and more data and more events. Of course, there are more challenges. So I just posed what are the interesting questions which we want to probe. Basically, the formation, binary formation channels, what are the properties of different systems, and which in turn can sort of give shine light on the formation. Also constraining the astrophysical merger rate, probing equations of state of the binary neutrons of the neutron star, and probe cosmology with the population. Um, right. So yeah, so that's the future. However, there are lots of challenges. So there are challenges on the front of detection. For example, we are not yet ready to. Our searches are just aligned spin searches. Okay, so the search does not include the generic spins. We have not included the eccentricity, neither the higher order modes. Mm, so these are challenges, and we are working towards to deal with those. Of course, as you improve the detectors, there are new kinds of noisy transients. For example, these are the different kinds of noisy events which creep into the detectors. So if you look at, so this is the intermediate mass black hole typical signature, and if you look at this event and this event, this noisy transient, which is a blip, morphologically they look quite similar, and many times these uh, signals or these noise transients affect our uh, searches, and essentially we need to try and figure out or develop veto strategies in order to ensure that what we are detecting is indeed astrophysical in origin. Of course, there are different ideas on in detection algorithms, such as machine learning ideas to sort of distinguish and attack these problems. There are different challenges for the estimation of parameters, because all these things which we can only do if we can accurately estimate the properties of the system. And there also, there is a lot of development on the front of, let's say, eccentric binaries. People are working on that with generic spins and things like that. Of course, there are issues of the waveform systematics when you compare with different waveform families, especially when you're looking at highly processing or high mass ratio systems. Um, uh, Further, there are future gravitational wave missions, and I think at this point I'm going to stop. So I think I'll take if there are any questions. I mean, this slide is just to show you that the prospect of gravitational wave astronomy is quite rich, and there are plans for basically space-based gravitational wave antennas, as well as the third generation Cosmic Explorer and Einstein telescope, which plan to probe the compact binary merger. Uh, yeah, till almost like whatever they exist so far. So with that, I will stop.